Welcome to our presentation. We are presenting for the Material Science and Engineering Senior Design Team sponsored by Wapaka Foundry, studying the effect of zinc on ductile iron microstructure and properties. My name is Amber Shaw, and I am our team lead.
I'm Chase Henderson, the metallography lead.
I'm Daniel Branagan, the casting lead.
And I'm River Maas, the mechanical testing lead.
So, to give a little bit of background, ductile iron is a hypereutectic cast iron alloy with spheroidized graphite nodules. The black bits being the graphite, the white around it, the ferrite, and the darker phase, the perlite. This is typically on the iron phase diagram, around 3 to 4 weight% carbon. This is a product that Wapaka creates. So currently, they utilize non-galvanized prime scrap steel. This is because it has a known composition, but it is a little bit more expensive. As such, they would like to utilize galvanized scrap steel. They have access to a large amounts of both prime and obsolete scrap. However, they have not been doing this due to the unknown effects of zinc. Some literature has suggested that zinc promotes the formation of ferrite in cast iron, which generally decreases strength. So both tensile and yield strength decrease with the increased zinc. So we created our hypothesis. If the zinc content increases, then the iron strength will decrease because zinc acts as a ferrite stabilizing element. So increase the zinc, increase the ferrite phase, and decrease the strength.
The goals for qualifying the effect of zinc this semester centered around metallography and hardness testing. First, establishing a zinc recovery method to get zinc into our melt, utilizing galvanized washers and adding that directly into the melt. Then, quantitative metallography and Brinell hardness data were collected, and finally, statistical analysis centering around the factors of weight% zinc and the section thickness of our cast step blocks was used in a factorial. 2 ductile iron cast heats were performed this semester using our varying zinc content factor. One pour was shown to have a lower than ideal copper content, but the other one was shown to have a more consistent one. Our DOE was set up to analyze the effect of cooling rate and zinc content, the cooling rate corresponding to the thickness of their step blocks, using the responses of graphite fraction and nodularity, ferrite fraction, and perlite fraction to analyze the effect of zinc. Our first pours, microstructures, are displayed. As zinc increased, generally graphite nodules became larger, and as shown on the board, the images were captured from the 20 millimeter step block that was cast. The lower copper heats metallography data did not show any statistically significant correlation between zinc weight% and the examination parameters of the ferrite and perlite fractions, as shown by the p-values. The scatter plots presented showed that zinc content also had a small overall effect on the perlite fraction, which was displayed.
And our quantitative metallography for our final heat showed visible differences with zinc content. As you can see on that left-hand image, the ferrite colonies are larger, whereas on the right hand with our higher zinc content, they are significantly smaller, and you can see that just with your eyes. The metallography for that final heats data showed statistically significant correlation between zinc and perlite fractions, as those p-values are 0.000, which is statistically significant. The Pareto chart also shows that significance, the top step block there is zinc content and the bottom is thickness. And this is just another data trend showing that it favors higher perlite fraction with smaller section thicknesses and higher zinc contents.
So we were able to quantify, it's a well-known phenomenon that zinc fades from molten cast iron melts, and we were able to quantify this doing what's called a fade study. So we took chemical compositions at various times, starting with zinc in the melt, and as you can see from the chart, the zinc content decreased over time. So the zinc content showed some effects on the melt as well. It showed that increased zinc led to decreased manganese content. That's because zinc oxide is less stable than manganese oxide, so it caused the manganese to oxidize out of the melt. And zinc also caused significantly lower sulfur in the melt as well. So our hypotheses predict that zinc acts as a ferrite stabilizer, but the findings suggest that zinc is actually a perlite stabilizer. Additionally, zinc interacts with and removes manganese and sulfur from the melt, and most zinc volatilizes before dissolving in molten cast iron.